Okay, welcome back, static students. Again, this is ENGR 214 ampersand BTC winter quarter 2020, and we are continuing on with mini lectures on trusses. So we left off with truss shortcuts, identifying zero force members and other things that made our method of joint solutions a little bit quicker and easier, to be used with caution and knowing that we can always default back to our standard method of joints and get the right answer. So we're going to take a quick look here now on general trends in number of equations and unknowns for our truss solutions. We're going to kind of focus on 2D as usual, but know that we can just easily expand it out into that third dimension by adding 3 equations of equilibrium per pin. So one of the big things we want to do if we're approaching a truss is to understand, before we dive into all the math and draw a whole bunch of FBDs, is can we get a unique solution for the force in each member and for the support reactions? Sometimes that's possible. Sometimes we might find it and find that nonetheless that we can't put the whole truss into static equilibrium, which might mean some of it can move relative to the other, and that's called instability, just another form of not being in static equilibrium, or lack of rigidity, because you can have one set of members accelerating, moving relative to the other. And so it's good to know that ahead of time and not get halfway into a complicated, cumbersome set of solutions only to find that, oh, we shouldn't have started. So we're going to review what it takes for a truss to be stable, rigid, statically determinate, so that we know that it falls within the realm of statics. It's not going to accelerate. It's not going to deform, deflect relative to itself, and that we can get one solution for the force in each member. If something is indeterminate, that doesn't mean that it's going to accelerate. It's still definitely going to be rigid and in static equilibrium, but we will typically have an infinite number of potential solutions for the forces in each member. We might know, we might be able to relate the force in one member to the force in the other, maybe by some sort of mathematical relationship, probably a line equation, but we won't know those numbers exactly. And so if we're designing something, we won't have an actual quantity that we could say compared to the strength of a material with a given cross-section. So we'll be looking at equations versus unknowns based on number of pins, number of members. So as we know from having stepped through the method of joints, the total number of independent equations in a truss is going to be 2 times the number of pins if we have a 2D truss. And it's going to be 3 times the number of pins if we have a space truss, because each pin gives us some of the forces in the X and Y or the X and Y and Z. No moment about those pins, free spinning, or we don't have a truss. So that's the number of equation, 2 times the number of pins. The number of unknowns is the number of members, because that's what we're solving for. So if the number of equations that you need for the support reactions is 3, which is pretty typical for what we call the simply supported trusses in 2D, and this entire argument is 2D at this point, then we can say that the maximum number of members whose forces can be determined, and that's determined explicitly with a number, not just a relationship to another force, is 2p minus 3. So we can say m, the number of members that we can uniquely solve for, is twice the number of pins minus the number of support reactions. So that's basically the number effectively related to the number of equations of equilibrium in the pins, remembering that some of those support reactions end up giving us a check equation, so that's where those actually get subtracted out in that 3. If a truss has more than m members in it, that means we can actually constrain it more. We have more ways to keep things from moving, and in that case it would be called statically indeterminate. It's not going to accelerate, it's very stable, might be overly stable from a fracture standpoint, but we can only maybe relate the force in one to the force in the other. We can't get a unique solution for the force in each member. If the truss has fewer members than the 2p minus 3, so we got too many equations and not enough unknowns, the truss might not be rigid, and that's just another way of saying that all parts of it will not be in static equilibrium, and that's bad if we want it to stand up. So let's see if we can spot these in some examples. So this looks an awful lot like something we've done before. So let's apply that relationship to this truss. We're going to start with number of support reactions. We can apply 2 here and 1 there, so that's 3. Number of support reactions is 3. And let's count the pins. We have 1, 2, 3, 4, 5. So 2p minus number of support reactions is 7. How many members do we have? 1, 2, 3, 4, 5, 6, 7. That means it is both rigid and statically determinate. So we could go through and use our method of joints, or any other method actually, and find a unique single force that each member carries. And in fact, we've done that. This was our first example, a truss that looked just like that. Okay, let's look at this one. Again, we have 3 support reactions. And we have 1, 2, 3, 4, 5 pins. So we would need 7 members, just like in the other one, for rigidity. And if we had more than 7 members, we would be statically indeterminate. Well, we're missing that top member, so we only have 6. So we're not rigid. And in fact, just thinking about this just kind of intuitively, since you've got a downward load here, and a moment being applied around this pin via this force, unless these 2 forces happen to balance just perfectly, it's very likely that this hinge will deflect and the truss will either collapse downward or it'll rotate outward. And that's definitely not what we want. So this truss is not rigid. Rigidity, I guess, if you want to think about it, is a way of saying that you are susceptible to not being in static equilibrium, because I guess you could say that depending on the exact values for the applied loads, you might not be accelerating. But rigidity in the sense of trusses says it doesn't matter what the applied loads are. I will not be accelerating. I can be in static equilibrium irrespective of the applied loads by simply changing the values of the forces in my members, provided that I don't exceed some material property. So I guess rigidity could be thought of as the potential for not being in static equilibrium, depending on external loading. So I like to think of it as just having a static equilibrium deficiency. But I should point out you could have that sweet spot of applied loads that kind of keep it from collapsing, but that doesn't quite count. Okay, going to the other end, somebody's added another member here. I guess they felt that we needed additional rigidity. Did we? Well, let's do our count. Number of pins: 1, 2, 3, 4, 5. So 2p is 10. We still have 1, 2, 3 support reactions. So 2p minus number of support reactions is still 7. And 1, 2, 3, 4, 5, 6, 7, 8. We have an extra member. So this extra member that somebody placed in here was not necessary for rigidity, and now we are statically indeterminate. So that means if we just applied method of joints or method of sections, we would find that we could probably only solve for the force in this additional member in terms of the other forces. We could not get a unique solution. So again, general rule, the number of members that we need to have a unique solution to be rigid, statically determinate, is 2 times the number of pins minus the number of support reactions. So we can apply that to that concept of simple trusses that we started with when we first started the truss section. So we go back to the definition of a simple truss as a triangle in a plane, or a pyramid if you're in 3D. That's like your unit cell, your most basic element of a truss. We don't have support reactions. We've kind of decoupled this from supports. It's just kind of floating around. So we could apply the same number of pins and number of members and say, hey, the number of support reactions is 0. So we start out with this one having 3 pins and 3 members, and we're going to use the method of adding pins and connecting back with members to continue to create a larger and larger simple truss. And that's how you continue to keep a truss quote unquote simple, is by making sure you just have these additional triangles. And you'll add a pin out someplace in space, doesn't have to be equilateral or any particular position, but you'll add a pin to a simple triangle or another pin to a simple pyramid, and then connect that new pin back to the existing simple truss with, if you're in a plane, 2 members, or if you're in space, 3. So we add, by adding pin C, we've added 1 pin, so P equals 4, which is 3 plus 1, and we've added 2 members, so 3 plus 2 is 5. If we keep doing that, adding another point, C and D, we notice we get a formula that should look hauntingly similar. If we look out and keep adding more pins and more pins, and counting the number of members that you get by simple truss growth, by adding 1 pin connecting back with 2 members, or adding 1 pin connecting back with 3 members for a space truss. So if you build a simple truss, you will end up automatically finding that the number of members that you have meets the static determinacy requirement and rigidity requirement, 2p minus 3. This doesn't count support reactions, so it's just sitting there. You could apply loads. You could apply loads indirectly that are reacted on by some kind of support reaction. You'd be rigid, and you'd be able to find a unique force in each member. So this is one reason that the simple truss style and design method is popular. You know you have something that is statically determinate and is rigid. And just as a note, simple trusses don't always look simple. This is a simple truss. You've got something that looks very familiar with the equilateral triangles. Somebody stuck a point out here and joined it with 2 members. Looks weird. It's still a simple truss. P equals 6, M equals 9. So 2p minus 3 is 12, minus 3 is 9. Meets that 2p minus 3 criteria. You can have more than 3 support reactions. Just because a truss is out there doesn't mean it's going to be simply supported. So here's an example of what would otherwise not be a stable truss that is rendered stable by having an additional support reaction. So you look at this, you've got a couple of simple trusses that are joined by a hinge. Normally we would need a member joining them here. So you have P equals 7 and M equals 10. So you do your 2P is 14 minus 3 is 11. We're missing a member. If we're missing a member, that means we're not rigid, and it's really easy to see that. So if say this support reaction were our typical roller, this point would displace, the whole thing would collapse flat. But our number of support reactions is not 3, it's 4. So 2p minus the number of support reactions really does tally up to the number of members. So do not memorize 2p minus 3 unless you have simple trusses. You could have something that is different, and the additional rigidity is being provided by the support reaction. Now that said, you better not take this off its supports or it's going to collapse flat. So that's something to look at. So if you're going to analyze this, you would definitely be expecting to need this to provide some horizontal force, depending on how it's loaded. And almost done with this one section here. We'll throw out one more vocabulary term, the word compound truss you might run across, and that's defined as 2 or more simple trusses connected to give a rigid determinate truss. So this one up here, even though it's 2 simple trusses, it doesn't combine to give a rigid truss. It's being given functional rigidity by dint of the fact that we have an extra support reaction. But if we put an extra member here, then we would have a compound truss. We'd have 2 simple trusses connected. And those are, from a manufacturing standpoint, sometimes very easy, that the 2 simple trusses can be made and then connected, possibly on site. So something to think about. This gets into application specifics both both in small parts that you might run across for manufacturing, but definitely this has applications for structural engineering for buildings and bridges and other large civil structures. Okay, so we have now looked at what is a truss. We've looked at simple trusses. We've looked at rigidity and static determinacy. We've related it to number of pins and number of members, thinking through what it means to be solvable mathematically with number of equations and unknowns being represented by pins and members respectively. And we've gone through several examples of method of joints, one which included a happy shortcut that we were able to correctly apply with a zero force member. So the last subtopic that we'll have with trusses will be the method of sections. And so that'll be really useful when you want to get the force in one member. Something to remember with method of sections is it will require a little bit more finesse. You'll have to make some judgment calls on where to put your section, but otherwise it's just more equations of equilibrium. And know that if you need to find the force in any member, in any truss, you can use either method. And as a suggestion, the method of joints, as cumbersome and long-winded as it is, tends to be simpler. It will always get you there. So we'll do some practice with method of sections, and then on any homeworks or exams, unless you are specifically directed to use one method or you are asked about the consequences of using one method, it's up to you. So you are on your own recognizance. Pick the method that works for you, as of course you will do when you are out on the job, hopefully deploying this. So that is it for now, and I will see you for the next recorded lecture on method of sections.